So we are getting started with quantum phase estimation. This is recorded. It's not live because I am probably flying right now. We might do 2 hours, a bit more, a bit less. I don't know. We'll see. But today's session is going to be focused on quantum phase estimation. So I did QFT last week. It was a bit bad with the connection. Now he is better, but anyway, because I'm not doing it live, it should go smooth. And quantum phase estimation, I did that. I covered that in the channel before, but I haven't revisited it for quite a while now. So I'm curious if my intuition is still fresh. Now, let me think how to approach this, because I see it seems to be so. There's one chapter here called intuition, which is pretty. I'm pretty curious to go through. But first, maybe let me try to refresh a little bit. So, if I remember well, this is just actually this is just an application of QFT, really. Quantum phase estimation. It's called phase estimation because I think it can generalize the usage of it, as in it estimates the phase of an operation or something like that. Like if I go to Quirk and basically I pick any operation, right? So these operations you can see here, they all have a global phase, and I think that's the phase this thing estimates. If I remember well, but let's see, quantum phase estimation. So if I remember well, this is just, so that's the circuit, but I mean, it's really just QFT. So basically, I cannot paint on that because basically I think this is as simple as, so you see here's QFT and here you've got a superposition as the initial state, right? And then that portion in between, so all the stuff that's in here, this is really just preparing the state you wanna, preparing the input for the QFT, or the inverse of the QFT. Remember that we in the past video we talked about the fact that the QFT, one of the things the QFT is doing is encoding and decoding a phase encoded wave signal, right? So if I want to have, for example, if I apply the QFT, right, and I give it a 1 as an input, it basically encodes it creates a superposition where the phase encodes a wave that kind of, within the amount of available data, it gives a full circle. Because it's a 1, right? If I put a 2, then it's going to do 2 circles, right? So when we're basically, oops, sorry, my hand in the middle as usual. So when we're, how am I going to do this? So when we're when we're here, so this is one cycle, this is another cycle, right? It's counterclockwise. And so the inverse does the opposite, right? So it takes something like these and it gives you the frequencies. And so all this is doing is you're preparing the data, you're encoding the data in the phase of your superposition. That's essentially, if I remember what was doing. So, but let's see how this is presented here. And I don't know if we're gonna need. And I come down. Let's just get started with that anyway, just in case first. So we're gonna go into the workspace and basically go into the Qiskit reading session group, and then create another called session 6, and then basically go into session 6 and Jupyter Notebook. So this is definitely, so let's see if that starts the whole thing. So let's get started. I mean, overview. So quantum phase estimation is one of the most important. I hope we're gonna Oh, here you go. Here we have the notebook. Okay, I'll try to move my camera around so it doesn't bother, but it shouldn't bother here right now. So a quantum phase estimation is one of the most important subroutines in quantum computation. It serves as a central building block for many quantum algorithms. The objective of the algorithm is the following. Given a unitary operator, the algorithm estimates alpha theta in U applied to this state equals, yeah, so this is, okay. So as in U, here this state is here this is an eigenvector, and this exponential here is the corresponding eigenvalue. Since U is unitary, all of its eigenvalues have a norm of 1. That doesn't help me. It doesn't help me. You see, for me, it's a bit more like knowing. So it seems it's because it's the same circuit. So for me, it's a bit more like a more practical definition, which is by far a generic one. And I'm giving here specific feedback to just that part here, right? So is that basically QFT is a protocol of how do we encode something into a phase, into a superposition. How do we phase encode something, and then we read this out with the QFT, because that's the idea. Is the QFT allows you to read these out, but again, I might miss because when I'm not so sure if I went deep enough when I did my breakdown of the QP, or the quantum phase estimation. This is still a pretty, I think, a bit fuzzy to me, right? It's this definitely, it's got a lot to do with the phase kickback. But I always thought, as in, you're doing an operation and then you're encoding the result in your superposition somehow, in the phase of your superposition. That's the way. Because this U thing here, this box in here, can be like an arbitrarily long operation. It's not like an X gate or whatever. I mean, you could, right? You could just use a T gate or an X gate or whatever, and you're kind of estimating its phase. But you can do something more and then encode. You know what I mean? It's just these really doesn't have to be that generic. It can just be something you're. If I go to the to Kindle, to basically the to this guy here, so to the how's the book called? Yes. So here they have a section on phase arithmetic or something like that I found really cool, because it's not explained anywhere else. Phase encoded results, getting really quantum. I think this is these. So this is really interesting because it basically walks you through an example or an idea where you could encode results in the phase by just applying rotations that are proportional to your results. So you've got your phase that allows you to basically encode these data within your 360 degrees, right? And that's all this. I think that's a far better explanation, or something that's a bit more practical. I mean, I get that's definitely correct, but it's the same pattern. It's the same that I made, the same comment that I made for the QFT. That's basically coming from my perspective really top down, right? So, but that's one thing. Okay, so overview. So we get the circuit in here. I mean, this circuit is really, it's simple, right? So you've got the QFT or the inverse QFT. You've got that part in here. That's you've got that part in here. That's the input preparation or the encoding part. That's just preparing the superposition. Yeah, and then the readout. So Okay, so let's go through the intuition. The quantum phase estimation algorithm uses phase kickback, okay, to write the phase of U in the Fourier basis. It's the first time I see it written this way, the Fourier basis. As if you could use the QFT to encode data, but I mean, that's actually what I talked about right now, right? So you say, for example, the number 1, the number 2, right? It's this in Fourier basis. That's what I think this means. So this would be the Fourier basis, right? And that's number 2 in Fourier basis. Okay, I think. That's a nice way to put it, yeah. To the T qubits in the counting register. We then use the inverse QFT to translate these from the Fourier basis into the computational basis, which we can measure. Yeah, you see, but that's that's a far better explanation of what QP is. Okay, but it would be nice if you introduce what I mean by Fourier basis. I mean, I think I could deduce this based on. Okay, so maybe so that's how you. Okay, so that's basically we remember from the QFT chapter that in the Fourier basis, the topmost qubit completes one full rotation when counting between 0 and 2 to the power of t. To count to a number x between 0 and 2 to the power of t, we rotate this qubit by x divided by 2 to the power of t around the z-axis. For the next qubit, we rotate 2 times x, then 4 times x. Yeah, so that's what I mean. Yeah. Okay. So you're rotating in a way that's proportional to the number that you're representing. Yeah. And that it's governed by the so 5 in the Fourier basis on 3 qubits is 5 divided by 8. 10 divided by, in the first qubit is 5 divided by 8, then it's 10 divided by 8, and then it's 20 divided by 8. Yeah, and this is all rotations, okay. When we use a qubit to control, so when we use a qubit to control the U gate, the qubit will turn due to kickback proportionally to the phase. But proportionally to what phase? To a phase. We can use successive CU gates, control U gates, to repeat this rotation an approximate number of times until we have encoded the phase theta as a number between 0 and 2 to the power of t in the Fourier basis. Then we use simply the QFT inverse to convert this into the computational basis. Okay, that's not bad. That's not. I think it's okay. That's pretty nice actually. I like it. The thing here with the Fourier basis, this seems like, if I was reading this, it seems like this is sort of something already introduced in 3.6, but I don't remember reading anything about the Fourier basis in here. No, nothing. Fourier basis. No. So let's go ahead. But not bad. I quite like this, the way that this is explained. So let's try that actually. For example, 5 in, so let's clean this up. 5 5. What am I doing? Clean everything. So 5 is these, right? 5 is these, correct? So that's the Q. That's what we're getting in here, right? So is it 4 5? Yeah. 5/8 full turns. 10/8 full turns and 28, but those figures definitely match these ones in here. Let me zoom in. So there you go. There you go. That's an interesting way to see these, actually. That's an interesting intuition, because that's basically saying, so you're rotating random from the QFT, because this seems like this is explained in 3.6, but it's not explained this way, I think. The Fourier basis, the topmost qubit completes one full rotation when counting from between 0 and 2 to the power of t. To count to a number x between 0 and to the power of t, we're rotating yeah, that's actually interesting, because if we would do these, the topmost qubit, that's this one, I guess. It almost gives a full rotation, right? So yeah. So then to rotate the number of x, it's x divided by 2 to the power of t around the z-axis. And then each qubit is its power of 2. That's just it's nice. I'm didn't think about it this way, because I was always thinking at the system level, and this is kind of at the qubit level, how you would translate something from the computational basis to the Fourier basis. I like these. Okay, and that defines in turn your super. But it's a nice way to see this. That's cool. It's cool. Mathematical basis. I'm not gonna like these, I guess. Then example. So what do we have? Mentioned above, the circuit estimates the phase of a unitary operator U. It estimates theta and these, where there's an eigenvector, value. The circuit operates in the concept of eigenvectors and eigenvalues here don't really bring anything to the explanation right now. I think setup is, so phi is one of the, or whatever this is called, is one set of qubit registers. An additional set of n qubits from the counting register, on which we'll store the value 2 to the power of n times theta. Okay, so this is the superposition. Apply an NB Harmonic gate to the counting register. Then controlled unitary operations. We need to introduce a controlled unitary CU that applies the unitary U on the target register only if its corresponding control bit is 1. Since U is a unitary operator with eigenvector these, okay, so this just goes on with the math, and then applies the inverse Fourier transform, and then we measure stuff. So the above expression peaks near these for the case when this is an integer. Measuring the computational basis gives the phase in the ancilla register with high probability. For the case where it is not an integer, it can be shown that the above expression still peaks near these with probability better than 40%. Example with a T-gate. Okay, now we have an example. So let's go. Let's do this. So give me a second. So wait a second. Let me just. I feel I'm going to be fast. Let me interiorize one thing here. Where was that thing here with a phase proportional to kickback? The kickback. So when we use a qubit to control the U gate, the qubit will turn due to kickback proportionally to this phase. Let's check that out. So let's say we put ourselves in superposition, okay? So we'll turn due to kickback proportional to this phase. Let's say we put ourselves in superposition in here, right? And let's say this is the superposition. So let's say we're now gonna do these. An X gate is maybe the wrong operation. No, it says 90 degrees, but there's no phase rotation in here. What does it mean that the qubit will turn due to kickback proportionally to the phase? Yeah, but should this be in 1 or something like that? I'm not sure I get that. Okay. Let me fix that. Okay. I don't see anything in here. So this is 90 degrees. If I would put a Harmonic, I also don't kind of chance amplitudes. Yeah, I don't see that. Well, now it rotated. It rotated actually 180 degrees. It rotated 180 degrees, but the Harmonic should rotate 90 degrees. I'm not sure I understand. We use a qubit to control the U-gate. The qubit will turn due to kickback proportionally to the phase, so that we can use successive CU gates to repeat this rotation. Let's go through the example. Maybe that's going to be more helpful. So, example with the T-gate. Let's take a gate that we know well, the T-gate, and use quantum phase estimation to estimate its phase. You remember the T-gate adds a phase of pi divided by 4 to the state 1. So this is what we see here, 22.5 I, and pi divided by 4 is these, and I think basically 0.78 radians to these. I think that's 44. But why does this say exactly the half? It's 45 degrees. The global phase. Oh, no, rotates the phase by 45 degrees. 45 degrees. Sorry, it rotates the phase by 45 degrees. It rotates 1 by 45 degrees. That's the phase. So it's not the global phase. And it's not the global phase, it's the rotation. So it makes sense. The Harmonic is 180 degrees because it says rotates 180 degrees. Okay, so that makes sense. So we use quantum phase estimation to estimate this pi divided by 4, which is 45 degrees, to the state 1. Since QP will give us theta here, we expect to find 1/8. Okay. In this example, we'll use the 3 qubits and obtain the an exact result, not an estimation. That's cool. So it will give us 1/8, really. So if I do something, if we use 3 qubits, so if we use 3 qubits, right, and we use the T-gate, so this is rotating 45 degrees. This is rotating, so this we should do we should do twice t here, right? That's what I think the whole point is, because we need this to rotate more. Is that the point of the whole thing? I think that's the point, because it's, oh no, that's the one that should rotate the most, 2 to the power of n minus 2. So it's u to the power of 2 to the power of n minus 1. But what's n? It's the number of qubits, is it? I mean, let's see. Let's go ahead with Qiskit. So we've got these in here. We're gonna create a new notebook. We're gonna put it on the side. We're gonna choose this here. Close that, and cool. So, and I'm gonna put myself. If I can I move myself? Yeah, can I move my face? Yes. I'll move it up here so I don't bother you guys, and then I'll just copy paste that. So we've got all the imports and whatnot, and then now we set the quantum circle. We'll use 4 qubits, 0 to 2 as counting qubits, and 3 as the eigenstate of the unitary operator t. So we need to initialize. So we need to initialize the state as the state that will actually have an action. That the gate actually will. I think that's the point. Is this running? Am I not connected? No, I'm connected. Okay, here we go. So this is our. Okay, so this is our. This is where we're going to apply the operations that we control. We apply the harmonic to the counting qubits. So what are we doing? QPE, quantum circuit, QPE is X, and then draw. Okay, so then 4 qubit in range 3. We apply that, and we draw it. Cool. What does the next piece of code do? So the next piece of code does repetitions 1 for counting qubit in range 3 for I in range repetitions. Okay, so that's a controlled U1. Oh, come on, but you should apply a T-gate, shouldn't you? Ah, because is it because in Qiskit you don't have a control T-gate, I guess? Yeah. This is the controlled U. Okay. And so you're doing repetitions times 2, because for each iteration you're gonna have, okay, so okay, so first you control once, then you do it twice, and then you do it like 3 times. 4 times, sorry. Oh god. But isn't this sort of telling you the opposite? You start with like u to the power of, in this case 2, right? So this seems to indicate the opposite, but let's maybe again you're going to read the qubits in a different order. I don't know. So this is what this is doing. So we apply the inverse quantum Fourier transform to convert the state of the counting register. We apply the inverse quantum Fourier transform to convert the state of the quantum register. Here we provide the code for the QFT inverse. Okay, so there's the QFT dagger in here already. Don't forget the swaps. Yeah. So now in theory, so what do we, let's see, what happens if we measure now? So what do we get if we, just out of curiosity, no, but if I was to measure that, it feels it's still faster in Quirk. So, but I'm gonna use Control T's in here. So now I'm gonna do basically, I'm gonna basically do these and basically do it like that. So that's kind of the same, right? And if I now take a look at these, if I just take a look at these amplitudes, so you've got, it's cool because you've actually got the one, right? And maybe that's, so this is definitely one in the Fourier basis, and because it's giving you a one full circle. And so this is then probably, it means that you're getting the numerator of these, because the 8 is definitely your precision, right? So because it's, you've got 3 qubits, it's 2 to the power 3, it's 8. So I'm guessing this is the whole thing here. Because now if I go and I apply the inverse of the QFT, then bam, 001. So that's what you got. So QFT, what am I doing? So okay, so creating the circuit, we're doing that. So let's go. We've got the QFT dagger in here, and we then measure. Okay, so this adds a nice barrier and whatnot, and then inline backend from PNG stops the images getting too big. Ah, okay, that's interesting. There's no way I remember that stuff though, honestly. Unless I'd be working with this every day, there's no way I remember all these. Okay, so you've got in here, then you've got the QFT, and then you measure stuff. Get the results, especially getting the results. I keep forgetting that, but yeah, 001. That's also what this guy is telling us here. Cool. So we see now we get one result, 001, which with certainty, which translates to the decimal 1. We now need to divide our result by 2 to the power of n to get theta. Getting more precision. To get more precision, you probably want to get more qubits. But if you want to get more qubits, then you're going to do even more times the controlled unitary. So it's going to be expensive to do that. So instead of a T gate, let's use a gate with a 1/3 theta. We then set up a circuit. Okay, so it's a whole different thing here now. Yeah. Okay, so I guess the point here is once you do that, you're going to see there's not enough precision because you're not going to get certainty. The more precision you've got, the more certainty you're going to get, I guess. And so it's either 2 or 3. So if we replace that by what is these? Open new tab. It's 2 pi divided by 3. It's just 2 divided by 3. That's 2/3. So if I use in Quirk instead of these, if I use Z gate, like if I use is a parametrized Z gate, that basically does 2 divided by 3, right? And I do this like that. Here, put them here, put them here, put them here, put 2 more, so 1 here and 1 here. And I'm kind of getting the same, so it's 2 and 3, right? So, and what now though? I mean, what's the point of these? We're expecting the result 0.33, and we see our most likely result is 2 and 3 decimal. These two results would tell us 0.25 and 0.37. So it's really, so true value lies in between those values, but he doesn't certainly any precision. The solution, add more qubits. Yeah, but if you add more qubits, then you gotta do, okay, that's big. So we're adding 2 more qubits, but then we gotta do a lot more times the operation. It just increases exponentially. So the so the is it gonna try it? Yeah, nice. Yeah, because that's 2 to the power of 4 what you need to do here. So that's like literally 16. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. This is 10, 11, 12, 13, 14, 15, 16. Yeah, of course. You need it 16 times. Yeah, and then you decrease this. And so, and now if you take this and paste it, then we're gonna get the histogram, which is exactly almost like this one, for the number, which is this one, probably 1010, which isn't it? What is this? 1010 is decimal 10 and decimal 11. So this is between 0.34 and 0.31. So this is way more accurate. Okay, so it's way more accurate. So that's how you do it. And then real device data. So we're not gonna do this, but most likely result. Okay, so it's way noisier. Yeah, it's way noisier. Exercises. Try the experiments above with different gates. C naught S D dagger. What results do you expect? What results do you get? Try the experiment with a Y gate. Do you get the correct result? He wanted to make sure this is the instead of Y. Yeah, that's the point here. I think I think when you that was my whole point. Let me put that back. Put myself back here down there. So when you're this is going to be the eigenstate. So what this really means is that this is going to be a state that you know that gate affects from a phase perspective. This means that it actually rotates the phase, but it doesn't change the state. That's the point, I think, of this being an eigenstate. But that could be explained, right? So this is one. So if I put a 0 here, for example, or a minus, right? Like we're getting crap in here. That's definitely it only works with 1, right? If we're even if you're putting a 0, you're not getting any close to what you want. The reason is that the phase kickback is not working, because the point of the Z rotation is that there is that one state that it acts upon without touching it. So you could think of this as, let's put it this way. So you could think of gates affect both the phase but also the amplitudes, right? Or not the amplitudes, but the value. I don't know how you would say that, but there's always this one particular input state that stays unchanged. Yeah, okay, but that's maybe the wrong way to say it, because this also stays unchanged, but the phase is not, the phase is not changed. So there's just that particular one state where the gate will basically kind of apply a particular phase, and that's the characteristic phase of that gate, and that's maybe why you would call that the eigenvalue or the eigenvector or whatever, the eigenstate or eigenstate. Yeah, that's the, because these guys have here a more also this eigenstate. I think they have a nice explanation. So here's these exactly. So this was really cool to read as well. They explain really the concept of what an eigenstate is by using the Hadamard and saying the Hadamard. So take careful of note how Hadamard acts on these states. The first is completely unchanged, while the second only acquires a global phase of 180 degrees. The relative phase is unchanged. States impervious to a certain QPU's operation in this way are known as the operation's eigenstates. Yeah, and every operation has a distinct and unique set of eigenstates. So those are eigenstates where nothing changes, but just a global phase. But I'm not so sure if that's then true for, although the global phases that can acquire, they do teach us something relating about the key vibration producing them. The global phase acquired by a particular eigenstate is known as the eigenstate's eigenphase. Yeah, so this is the, maybe expanding a little bit more on these would be helpful. So if you want to do that with a Y gate, right? So a Y gate rotates 180 degrees, right? So if we want to replace all these for Y gates, right? Let's try to do that. So if we replace this with Y gates, I guess so 180 degrees, this means that this kind of rotates, what, pi? So if this rotates pi, and it should give us theta, right? So I think what this means is if it rotates pi, does this mean that theta should be 1/2? Yes, theta should be 1/2. So, because if you equal that to pi, that's how you would then find theta, I guess. So 1/2. So we should also see a 1 in here. That's the point. We should also see a 1 in here. So if I use the number 1, you're not seeing the right results, because the eigenstate would be, my intuition tells me, either I or minus I. So with I, not really. And with minus I, also not really. What's the eigenstate then? Interesting. Why? So minus I. Think should be minus I1 maybe then. Why? Because this definitely changes also 1 and 0. So that's, so what would be the eigenstate in here? This is basically, would the eigenstate be I think the eigenstate here, it's something like, so we first go to 1, and then we apply a phase of 90 degrees, so it's like what, an S, and then the amplitudes here are, so if I go here, is it these? It's not really these, right? That's not either. What about a set gate? I'm just playing with the idea here, okay? What about a Y gate? Also not. How can I figure this out intuitively? So the T gate. So what is the Y gate? What is the Y gate doing? So the T gate adds this phase to 1. So the Y gate is adding a phase of minus I to 0. Now transforms 1 into minus I. Transforms 1 into minus I. How would I translate that into a... that's a tough one. So... So it should be... Okay, so what if I now apply minus I? So minus I would be a Z a minus T minus S rotation, right? And now another X gate. So it's 0 minus, yeah, that's minus I. But it doesn't seem to be this. That's not the result that we want, right? No. What I? It's also not the result that we want. Minus I. What's the... So what's... Okay, let's take a look at clean version of Quirk, and let's take a look. So we're looking for a state where Y only adds a global irrelevant phase, right? So 0 turns into this one here. So 1 turns into that thing. So I'm guessing this will have to be actually somewhere in here, where if I take a look at the amplitudes, they are in phase, but here they are out of phase. So what if I now... Yeah, look at this. So this might be the case. H and S, let's give it a try. I mean, it's because it leaves the state untouched. That's why I'm guessing this might be it. Harmonic. Yeah, the trick is because you're in superposition. Because the trick here is the Y gate messes up with your 0 and 1s. It actually negates them at the same time, like it adds phase as well. So if I do a Harmonic and a NES gate, that's not exactly what I expected. Nope. And minus S, also not. What if I apply a Harmonic and a Y gate? Also not. I apply Harmonic and T gate. What do we have here? So we've got phase 0, phase 45. No. So now we've got... No. maybe these in a NAS gate. Oh, wait a second, could work. This has a, yeah, this just adds a global phase, I think, because this is basically phase 0 and phase minus 90. So there's like 3/4 difference, and here it's phase 180 and phase plus 90, and there's also 3/4 difference. So the relative phase is the same, right? Is the state 1, then a Harmonic, then an S. So 1 Harmonic and an S. Oh, come on. That's not it. That's not it. Or is it? Because this is a 3 and this is 12. No, this is a 4 and this is 12. This is a 4 and a 12, and we say the Y rotates 180 degrees. So we're looking for a phase of pi. Phase of pi, and this is 4. So 4 divided by 8, right? It's basically 0.5. Sure. Why am I getting this? And 12 divided by 8, 1.5. No. So it's not that. I guess it's pi, right? The answer. How would you do that for a C0 though? Try the experiments above with different gates, the C0. Okay, meaning the not. So, and you're doing control nots. Okay. But maybe the C0 will help me understand the Y gate, because the C with the control knot. So what's the, with a control knot, there's a phase of 180 degrees. Is the same thing, right? So the control knot, I think the eigenstate of the control knot is the Harmonic. It's the plus state, sorry, my state. If I, so I'm not that far, because if I, let's replace all that. Let's replace all that by control knots. Control knots, control knots, control knots, control knots, control knots, control knots. And let's have Harmonic. Oh, come on. I'm taking a look at the wrong thing here. This is the result I should take a look at, not that crap here. Okay. So it's 4. So 4 divided by 8, it's 1 divided by 2. So, and that's exactly what we want, because it means it's pi over 2 theta, right? It's pi over 2 over, I don't know if I'm using the right naming in English. It's pi divided by 2, because that's what we're looking, because if, come on, where are you? We want these to be 0. So for this to be, sorry, we equal these. So this has got to be a rotation of 180 degrees. That's what this is doing, rotating 180 degrees. So 180 degrees. So for this to be 180 degrees, which is pi, basically it means that theta has to be shouldn't be 1 divided by 4, though. So if this is, if t is supposed to rotate, pi divided by 4, if t is rotating pi divided by 4, then a knot is rotating. The knot is 180 degrees is pi. So this means what am I doing? It's a bit late. So if I want these to be pi, yeah, this has to be 1 divided by 2. That's all fine. That's all fine, people. That's all fine. Basic things. Yeah, so that's it actually, because this is 4 divided by 8 is 1 divided by 2, so we got it. So the Hadamard, but with the 1 and with 0 also? No. Interesting. So the minus state is the actual eigenstate. Okay, so with y's, I should be kind of almost the same, right? I should just maybe add a minus y phase to that. So I think the s and that should work. So if I now do this with a y, so if it's a Hadamard and an S gate or a minus S gate, no, that's not working. Sorry, not a minus. Wow. No, that's not. The 0 is not what we want. Yeah, we got it. That's it. It's that state. So it's basically the state. It's that state. It's that state here. You can see the screen right now. 0 minus I 1 divided by the square root of 2 or something like that. Okay, but that's it. So that's the exercise. Yeah, that's 4 because it's 4 divided by 8. It's 1/2. That's what we want. That's what we want. So it's really the game of finding, you got to find the right state in here. But let's use, how much time have we got left? It's been now, I think, about an hour. Is it? I think it's just been about an hour, and I think we're done with this. But let me maybe walk you through some of the stuff that I did before the QFT with the QFT, because the QFT is really okay. But wait a second. Let's go through these. Experiment with real devices. We're going to skip that. Exercises we've done. C naught and Y. Looking forward, the quantum phase estimation algorithm may seem pointless since we have to know theta to perform the control your operations in our quantum computer. We'll see in later chapters that it is possible to create circuits for which we don't know theta, and for which learning theta can tell us something very useful, most famously how to factor a number. Exactly. So now let me give you maybe a sneak peek on these, because I think there's no Shor's algorithm in here. That's quite interesting. Because really, you're almost there, right? Shor's algorithm is nothing else than QPE, just with some non-quantum stuff around it, but it's really these. The whole point of Shor's algorithm is that, and let me remove all this in here. But the whole point with Shor's algorithm is that maybe I'll show you actually. No, first I'll give you my sneak peek on this, and then I'll show you what is built in Quirk as well, which is pretty cool. So the whole point of Shor's algorithm is that this is all nice and whatnot, but you basically, the whole point is that if you do some sort of repeated exponentiation of a certain set of numbers, these things basically, they generate a cycle, right? So I don't know, say 2 to the power of 0, then 2 to the power of 1, then 2 to the power of 0 mod 20, 2 to the power of 1 mod 20, 2 to the power of 2 mod 20, and then you go through these, right? Because you're doing modulo 20. At some point, this keeps repeating, so you've got a cycle. the way you pick those numbers, this is something that I don't remember really well, and this is actually the actual Shor's algorithm lies in finding those numbers that you're doing these operations with. But if you basically keep doing these operations one by one, and you're phase encoding your result in here, you're and then you're and you're then going to find the how long. The thing is something like you're going to find that you're finding basically that kind of cyclic pattern in there, and then you use this number to do the factual factoring. So it's something like you have a bunch of in here. You do something like you multiply. Think you're multiplying. You're doing some arithmetic. You're multiplying. Let me see if I can get us some more qubits in here. So you're multiplying, just so I get the qubits in here. So you're doing some. Can I zoom out so I can paint? So you're doing some kind of arithmetic in here, and then this result is put in here as a sort of in a relative or proportional rotation, right? So you're doing the same here and the same here and blah blah blah. You don't do it like these. It's not that you have so many. You actually have, you could say, like one per each, but you're doing here like let's say you're doing here 2 to the power of 0, then 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, right? And this result is 8, right? So this is 8. So this 8, you encode that rotation in here, and because you're doing that sorry, I don't know how to put my hand, modulo whatever, like at some point this thing repeats, right? So you're basically encoding these kind of cycle in your phase, and then the QFT inverse allows you to find that cycle, so the frequency, and with that number you can then do some simple math and get to the factors of the number you're looking for. So it's fairly straightforward to explain. Sure, I think knowing QP, because QP is the only quantum stuff you do in Sure. So let me see what if I clear all that. Oh, come on. If I clear all that and I refresh, actually there is Shor's algorithm, Shor's period finding in here. Yeah, so this is the exactly. So this is what the whole thing is doing. This is really big, but basically that's the idea. You've got this big box in here. That's a gate that's doing something like the register times b to the power of the input a. What? Okay, that's something that I was not really. Oh yeah, really, because this is a superposition. So you're doing it to the power of, you're controlling it on the superposition. So you're controlling it on every single. Wow, that's really high level. Sorry for that. I think that's not easy to take a look at. Let's make a smaller example. So what I wanted to do is the following. So let's imagine you want to do some arithmetic in here. So let's imagine you want to do something times a modulo r, right? So how does this look like? And again, this is so this is something that you wouldn't find those gates as a standard thing, but it's just, something times a, like whatever this register has, times a. Let's say a is some sort of constant. I think you can define that constant in query by saying, the constant is going to be 2, right? Modulo r, so we're going to say R is also going to be say modulo 4, right? So this is just really, this is not standard notation. This is just a unitary that takes this input and multiplies it by 2 modulo R, right? And it outputs the result in here. So let's see how this looks like as an example. So if I say 1, so it's 1 times 2 modulo 4 is 1, is 2, right? So if I measure here, I see that it's 1. One times 2, is it really doing this? Times A, which A equals 2. If I change that to 3, decimal 1, decimal 2. If I change to 2, mod R, that's weird. That should basically do this, right? So anyway, that confused me right now. Multiplies the target by input A mod input R. Only affects values less than R. No effect if the multiplication would be irreversible. Okay, that makes sense. So this is probably not reversible. That's why it doesn't affect. Times 2 is probably not reversible. That's why it affects that. So there's some limitations in the way this works because of the reversibility, but that's out of scope for this discussion. But if you do it this way, so if we change that to 3, now it would be somehow reversible, I guess, right? Because of the 1, 1. There's no other way you can get that. I guess that's the point. And now what you want to do is you want to encode that 3 into your, say, how can I add more qubits in here? Into your phase, right? So let me take out, can I just take these and put it here and these and put it here, right? So now you want to encode a 3 in a rotation in here. And because this is a rotation of precision 8, you want to do a rotation of 3/8, right? And so how you would do that? How? So you basically now I think it's easier if this has the same precision like this one. So you would want to do it this way exactly and get rid of these. Just going to be easier to explain. Because now basically what you control, so you basically, if we've got a 1 in here, do a Z. It's something like that, right? So you're doing a, I think, 1 divided by 2. And this is, you're doing a full Z. Is it correct? I think we're missing another Z. Z in here. So you're doing basically, but you know what I mean. You get what I mean, right? So you're doing a based on this result, you're encoding a rotation here. So you want to say if this is a 1, yeah, well, aren't you? Yeah, that's actually QFT. What you're doing here really is QFT, right? Is it? Yeah, it's QFT. It's QFT, of course. You won. You won the 3. What am I going with all these though? Where am I going with all these? What I'm trying to go with all these is that that's what you would do here. Where am I? That's what you would do with each of these boxes. You would encode these results, and then you want to find that cycle. I think. Yeah, because then whenever you will get the next 3, right, you're going to be basically encoding the same rotation like here. Because you will do that repetitively. So no, this is wrong. This is wrong. This is wrong. I'm bad at this, but what you would do is you would say, oh yeah, okay, think quirk is cool. Because you can say, I think you can do something like that. Cycling gradient faces a target. Oh yes, faces a target by a cycling amount proportional to its value. Perfect. So it, no, that's not what I want. That's not what I want though. Input A. I want to do faces a target by an amount proportional to its value, but I want this number to be this input. Oh, here, look at this. Here I remember Z rotates the target by an input A divided by the precision, which is to the power of n. Yes. So these, exactly, so these, and this is now going to be A. So yeah, baby. But I want to take a look at the blocks here. So it's whoop. So now that's what I wanted to show you. So this is rotated now, what? 135 degrees. That's 3/8, isn't it? That's also what we see here. Or no, almost. But if that's 5/8, then 3/8 should be somewhere like that. Yeah, kind of. Anyway, that's my point, right? So you're doing but that's a nice tooling. You see, that's something you really can do. I don't know if you really can do this in Quirk, or you can actually compile that into an actual circuit. But this rotates this Z in an amount that's proportional to its own value. How would you code that though? This shouldn't be complicated. Shouldn't be complicated. Shouldn't be complicated because it should be something that's controlled on this number, right? So it's something like, if here's a 1, rotate a little bit more, rotate, and if here's another 1, rotate as well, but you rotate proportional to the precision. The precision is known up front, so you should rotate proportional, so you should always rotate proportional to like whatever divided by 8. That's what it's getting. Okay, so you should then do a rotation that's proportional to to the power of that number, I guess. So you would do something, what would you do? You would do a control a z, that's basically, you want to rotate proportional. So what you want to do, you want to rotate what, one, so this would be, these would be 1/32, like 1/32. That's 8 times 4, or is it 8 times 2 actually? So 16, what you want in here, and then that qubit rotates you, actually 1/8. But minus and minus, no. Hey, something like that. I don't know. I can't think clearly now, but something like that. So you would control that. Yeah, something like that. Yes. It's not 8, sorry. We have 2 qubits, man. It's 4. So that should be not 16. So that should be 1/8. And this should be 1/4. Shouldn't be the other way around. Oh man, I'm so lost. I'm so lost. So if it's 1, not 1/8. If it's 1 here, that should be easy. Come on. If it's 1, then you just rotate 1/4. If this is 1 here, then you rotate 2/4. Yeah, stupid. Yeah, now you got it. So that's it. Yeah, that's amazing. So you're rotating an amount that's proportional to these, right? So this is the way one way you could do it, or you can use Quirk's really cool tools here, which almost seems specifically just, this gate seems to be here just on purpose for that, honestly. So you use that input gate, which is not really a gate, and then you use that rotation. Yeah, cool. It's 135 degrees, right? If I do this, just it's 135 degrees, perfect. Yeah, that's it. And then what you do is then you do the next, right? So then you do basically, so then you take that and then you apply another, another time these, right? So you need to, wasn't that 3 though? So then you apply the same here. Yeah, I gave you input R. I know input B, sorry. Now you need input B. No, now you need input B. Input B. I don't have to do it this way. I think I can actually define a 3 here and then use the whole thing here. But so now it's kind of repeating. So taking the result, which is 3, and and then doing 3 times 3, right, which is 9 modulo 4, which should be 1, I guess. Yeah, and then exactly, and then we are doing input A, and we're applying the same gate in here. And so take a look at the block sphere, and we've rotated 1/4 here. Here 3/4. And if I now apply this, I think I don't have to. I think I can put a 3 in here, and I can use input A, and I can also use here input A. Need input B? Okay, sorry, input B. Need input A times B. What have I done? What have I done? So R is 4. R is 4. I am. Oh, this is what we're doing, right? This is what we're doing. Wait a second. Input A. Exactly. So this is input A, which is 3 basically. And so exactly. And so, and then it's using this input A for these. We got it. And then if I repeat the whole thing again, if I now say, do these again, show me these again, and please rotate this guy again based on these. So we're running out of battery or what? Oh no. Okay, so these. And now I'm gonna say input A is these. So we should be now at 3. So we're back at here. We're back at these here. If I just take a look, how does it look like? If I just take a look at these two here. That's an awkward thing. If I do the inverse QFT, I would get almost 0. That doesn't seem right. The blocks here is like these, then you rotate 3 proportionally to 4. Right. Something's not right. But anyway, you get the gist of it, right? So you're doing something. Oh, sorry. Sorry. That's not what I... That's not what I meant. This is supposed to be, yeah, in here. Yeah. Something like this. Anyway, you're getting my point. What's that? What's the time now? It's about an hour and a half, I think. I got myself lost in here, so I'm probably gonna dig into this a little bit more. But yeah, pause this for a second. That's the point, right? So you're doing something like that. So you're doing this operation, and then you're encoding these in the phases, and then you're gonna basically find that cycle. I think. I don't like it because I don't feel like I really touched it completely. But I'm really struggling with the timing right now. So this is not what I would. So let me see. So you're doing this in Shor's algorithm, you're multiplying, and then you're you're rotating proportional to that. So you're really doing these here actually. Yeah. So you're doing these here. You're actually putting your stuff in the Fourier basis, basically. There you go. So you're encoding that here, and that's it. You're just doing it like, because I'm probably missing qubits in here, but the inverse of the QFT, and you've got like 2 almost. Whatever that means, I don't know actually. That's the difference between these and these, I guess, but whatever. Forget all these. Anyway, you're doing something like this. So you can take a look if you want to go through this yourself. You can take a look at the channel. You can take a look at the stuff that's there. I got to do a revisit of these definitely, and I'll probably do a separate video on that. But to the actual textbook, it explains the core concept. So from that perspective, good. It introduces a couple of things here that I didn't think of in this way, like the Fourier Basis, etc., which is also nice. Some of the mathematics behind the example with the T gate. So we've done the exercises with a Y gate and with a C NOT gate or with a NOT gate. It's it's a bit confusing though that you maybe I'm reading the exercise wrong, but it's a bit confusing. You call it a C NOT because you should put probably the NOT gate because you need to construct the control S and the control T dagger, right? So you can, or you're really meaning the control NOT gate, and then you have to construct the control NOT gate. I guess that's I guess that here they mean the X gate, and then the Y gate is sort of the exercise that serves to understand or to explain the fact that you need to play with that initial state where the actual phase is applied. I guess that's the point. But I'm really missing here Shor's algorithm, all honestly. Yeah, anyway, I'd say it's not a complicated algorithm really. It's just, you need to get the hands on with this rotations concept and the proportionality of it. So the fact that you're, where's the kickback? So the fact that when you have a U gate and you do a control U gate, the qubit will turn proportionally to the phase, proportionally to that phase. That's how it will. And so it will turn. What is that? 5 in the Fourier basis on 3 qubits. Yeah. So here you're gonna rotate 2 to the power of 1, and here you're gonna rotate 2 to the power of 4. The amount proportional to these. So when you're doing Shor's algorithm, you're really doing these, and then you might really, and then you really need to do these twice in here probably. I don't know. It would be cool to take a look at Shor's algorithm again, but that's the gist of it. That's where this is going. So you're rotating, you're operating in here, and then you're rotating proportionally to the results of your modular exponentiation, kind of. But I think we've gone too far. That's definitely Shor's algorithms. It's not the point here. That's the point. Is phase estimation is just QFT really. It's just an application of the QFT. So you're doing an operation, and you're using the fact that with the phase kickback, these things rotate proportionally, and then with the QFT, you're reading out that proportion. So that's the point. That's the point. Cool. Yeah, I think I'll leave it here. Because I really don't want to jump into Grover's algorithm. That's the it's the one. That's my favorite one. And I'm quite interested in quantum counting as well. See what's this about. And then a bit scared because we're getting into actual VQE and QAOA stuff like that. So, 5 is interesting, and VQLS. Yeah. I don't know, but all honestly, it feels like it helps a lot that I actually spent quite some time on these way before. Like I actually have gone through all of these algorithms before by myself, breaking them down from scratch and without going through the math. And so this has been, it's not optimal because I'm definitely not super fit with all this stuff, but I think it's helped me build a lot of intuition that it's super helpful in understanding the gist of these algorithms. And so that's all there is really. The precision. So there's some good points with the precision in here. I like the way this is presented. I like the exercises, but I'm maybe lacking a little bit of more context in here, as in examples of how this could be used, right? What were the references here? Also also Nielsen, okay. Anyway, I hope that was useful somehow. It's a pity that I was not live, but at least you get good quality, I hope. And yeah, we'll see you next week. Yeah, next week we're going to do Kroger's algorithm. Cool. See you.